This problem asks for the electric field inside and outside of a cylindrical insulator which has charge Q uniformly distributed over its volume, which has length L and radius A. So with all these problems, we'll begin with Gauss's law, which says that the net electric flux through some closed surface is the integral of E dot dA equals Q in, so the charge inside that closed surface, over epsilon naught. First thing we have to do is pick a Gaussian surface. We normally pick something that matches the geometry. So we'll pick a little cylinder that's inside our big cylinder. It has radius r and it has length little l. So that's our Gaussian surface. Now we have to ask, what are we going to fill in for our equation? Our net electric flux through this little cylinder is going to be the flux through the top. That's going to be 0 because the electric field points radially outwards everywhere, and here the area points out, so no flux through there. Flux through the back face of the cylinder will likewise be 0 because the area is this way and the electric field is this way. So our net flux is the flux through the walls of the cylinder. So the integral of E dot dA across the wall of the cylinder, which is the integral of E times dA. The area vector points straight out, the electric field points straight out, so we have E times dA times cosine of 0, and that of course is 1. Gives us the integral of E times dA. E is constant at this constant distance, so we get E times the integral of dA. Integral of dA is A, so we get E times A. A means the area of the wall of our little cylinder, so that'll be 2 pi r times the length. So that's what we have for this part of the equation. Next we need to figure out what do we put in for our Q inside. This is a volume, so the amount of charge inside that little cylinder is the volume charge density rho times the volume of the Gaussian cylinder. The volume of our Gaussian cylinder is the volume of this little dash line cylinder, so that's going to be pi times r squared times its length. And the charge density rho is the net charge on the cylinder Q divided by the total volume of the cylinder, which will be pi times a squared times the length L. And we see that our pi's cancel. So now we'll plug this in for this side of the equation. 2 pi times r times L equals Q inside, which is going to be Q times r squared times L over a squared times L and our epsilon naught. And we dropped our E here, so let's put that back in. So now we'll solve for the electric field. E equals Q r squared L over 2 pi r L a squared L epsilon naught. What cancels? L cancels. One of these r's cancels with this r, and we have Q times r 1 over 2 pi epsilon naught over a squared L. I think we've got everything there. And then if we wish, we can write this slightly different way. 1 over 2 pi epsilon naught would be 2 times Coulomb's constant K, so we can put that in or not as we see fit. We could define, if we wanted to, a linear charge density, the charge over the length Q over L, and we'd get lambda times r over a squared. So what we see here is that the electric field inside the cylinder is linear as we go outwards from the center. So there's our electric field inside. So the problem also asks for the electric field outside the cylinder. So now what we need to do is, let's just redraw our cylinder here. Length L, radius A. If we want the electric field outside, let's draw our Gaussian surface outside. So again, we'll make a cylinder that has length little l and radius little r. So when we're outside, here's our Gaussian surface. We'll apply Gauss's law again. So the integral of E dot dA equals Q inside over epsilon naught. We can go through the same process as above to see that the integral of E dot dA is E times 2 times pi times r times L. Our charge inside is going to be the amount of charge that's on this cylinder right here, this part of the cylinder right here, which would be the charge density, lambda, times the length of our cylinder over epsilon naught. So the amount of charge on this cylinder would be the total charge per unit length, Q over L, times the length of this much. So we see that our L's cancel. And we solve for E. E equals 1 over 2 pi epsilon naught times lambda over R. And then if we wanted to, we could write that lambda was Q over L, or we can just leave it in this form. So we see that outside the cylinder, our electric field falls off as 1 over R. Now, if we wanted to graph the electric field, and we do often graph things like this, let's put on a coordinate system. So let's graph our electric field as a function of distance from the center of the cylinder. And let's put the radius of the cylinder right here. There's A. So we're linear inside. It increases to some maximum value. E is proportional to R. Then as soon as we get outside, it falls off as 1 over R. So E is proportional to 1 over R. And we see here as R gets very large, then the electric field goes to 0. And that makes sense because our electric field will approach 0 as we get infinitely far away. The last interesting place is right here at R equals A. So right here, the electric field is going to be 2 times K times lambda times A over A squared, which would be 2 times K times lambda over A. And we would get exactly the same result if we plugged in R equals A for outside the cylinder as well. So then that's our value right here. So there's our electric field inside and outside of a solid cylinder.